Okay, we have a wheel very much like the foam wheel that we've used in here, and we might as well take a look at one. So it's this situation here. We got this wheel and it's rotating about an axis through its center, and the wheel is like right here, okay? Maybe with a mass here, force of gravity acting downward. And of course, if the wheel was released, it would rotate this way, okay? Now, in this case, the wheel is going to have an initial velocity in this direction, so that the force is going to obviously tend to slow it. It's intuitively obvious that that's what's going to happen, but we want to develop the machinery that allows us to analyze that more thoroughly. Okay, well, we did a little calculation. We estimated that the moment of inertia of the wheel might be about 0.001 kilogram meter squared. It's probably a little higher than that, probably closer to 0.002, but let's just go ahead and use the 0.001. Radius of 12 centimeters, so we model the wheel with an XY coordinate plane, Y vertical, X in this direction, centered, of course, on the axis of rotation. So here's the position on the wheel, and it's stated, we state that the position is at the 300-degree position on the circle. Now remember, we measure angles from the positive x-axis counterclockwise, so here's your 300 degrees. Now if you want an acute angle to associate with that, obviously the angle here would be 60 degrees, wouldn't it? But we're not going to use that. We're going to use the 300 degrees. It's just more convenient. We don't have to worry about plus and minus, as you'll see. Okay, well, then the first question we want to ask is, what's the torque exerted by this force? What torque is exerted in this situation due to this force? Okay, well, we saw last time that torque is a cross product of the r vector with the f vector, where the r vector is the vector from the axis to the point at which the f vector acts, and actually could be to any point along the line where the f vector acts, but we'll take it just as it is here. So here's our r vector, here's our f vector, okay? Now, we'll talk more about the cross product, although we already have, but what we know, and what we should have locked in from what we did last time, is that the torque is the r perpendicular component multiplied by f. Okay, by r perpendicular, we mean the component of r perpendicular to f. Okay, so it's kind of like a dot product, or like what you do for work, where you project the one vector on the other and use the projection times that vector, except in this case, you're not using the projection, you're using the projection line, if you will, the perpendicular component of this vector along the line of f. Okay? Alternatively, you could do r times f perpendicular, and the pictures would look like this. Okay, the r perpendicular, the component of r perpendicular to f, to the line of f, and I'm not drawing the two vectors now with the same initial point, that's not necessary, although we wanted to do that to get used to the way the projection looks. We can extend the vector f, and we just project the vector r onto the vector f. So the projection of r on f would be a vector from here to here, but we're interested in the perpendicular, and the projection of r on f is the parallel component of r. Well, the perpendicular component turns out to be just the vector along the projection line. So the projection line goes from here to here. Right there is your r perpendicular. Now we could also project f onto the direction perpendicular to r. Okay? Now I did that a little differently, but it's the same thing. This time I sketched the tangent line to the circle at this point, which is going to be perpendicular to r, because r is radial. So I sketched the tangent line and projected f onto the tangent line, and right there is my f perpendicular. Okay, the purple. I'll notice that, and you can take it from there. I'll just make one observation. If you just look at what's parallel and perpendicular to what, you find easily that this vector, this angle here marked by red is the same as this angle here. And both angles, in fact, are 60 degrees in this case, but in general, these angles are going to be equal. So, in any case, this is how we calculate the magnitude of the torque. The direction of the torque, because torque is a vector, the direction of the torque is the direction of r cross f. Now, what's the direction of r cross f? Right-hand rule, put your fingers in the direction of r, that would be this direction here, if I've got it right, you know, the angle of the board and stuff. And of course, it could be this way, this way, this way, this way, if you can get your hand to go that far. But then you want to be able to turn the r vector toward the f vector, okay? And that requires that my hand be like this. If it's like this, the f vector isn't over here. The f vector is in the plane. So my hand has to be in the plane, and the palm of my hand really has to run perpendicular to the plane in order that I can turn my fingers from the direction of r toward the direction of f. And you see that my thumb is pointing into the board. So, by the right-hand rule, yeah, okay, I'm trying to read my own statement here. By the right-hand rule, that vector, you notice, is perpendicular to the board because it's straight into the board. Since these vectors are in the board, this vector is perpendicular to the board, so it's perpendicular to and into the board, okay? Now, let's go ahead and put a z-axis on this. If this is our x-axis and this is our y-axis, well, just to practice using our right hand, the z-axis has to be perpendicular to the x and y-axis, and it has to be in the direction of the, fingers in the direction of the x-axis, turn the fingers toward the y-axis. The z-axis has to be out of the board. Well, that's the way I've drawn it. I've drawn kind of a z-axis here, so we have the x, the y, and the z is intended to depict a vector coming out of the board, as may be viewed from up there somewhere. Okay? Now we determine then that this cross product is into the board, which is the negative z direction. Okay? So by the right-hand rule, for this particular configuration, for the r vector here and the f vector here, the cross product, which is equal to the torque, is into the board and in the negative z direction. Magnitude is the magnitude of r perpendicular times the magnitude of f, or if you prefer, the magnitude of r times the magnitude of f perpendicular, as I explained it, whichever way you want to look at it for a given situation. And that's it. That's the magnitude, and it's in the negative z direction. Now, at this point, I introduce the I, j, and k vectors. The I vector is a unitless vector of magnitude 1 in the x direction. The j vector is a unitless vector of magnitude 1 in the y direction, and the k vector is a unitless vector in the z direction. Unitless vector of magnitude 1 in the z direction. The magnitude is 1, so we call these unit vectors. And these unit vectors make it a lot more convenient to talk about vectors. Okay? Okay, well, then we get to the question, what is the angular acceleration? Okay? Well, you know, I kind of had to drag it out of people. You know, well, torque is analogous to a force. For rotation, torque is kind of the rotational force. And quotes around that because it's not a force, it's a torque. It doesn't have the units of force, it has the units of force times distance. So, torque acts like force, and moment of inertia acts like mass. Now, how do you put force and mass together to get acceleration? Well, you shouldn't have to even think about it. Acceleration is going to be force divided by mass, because you've done that about 10,000 times by now. in thinking through problems, I hope. Okay? By analogy, the angular acceleration is going to be torque divided by the moment of inertia. Now, of course, last time we did write down the Newton's second law for rotation, which says torque equals moment of inertia times the angular acceleration. Okay, but you haven't really internalized that. So right now, I say use it by analogy. This is like mass, this is like force. You divide force by mass, you get acceleration. Okay, well then, what is this acceleration? Well, the torque, well, let's calculate it. Okay, our perpendicular in this case would be 12 centimeters times the cosine of 300 degrees, wouldn't it? Because look here, you have the circular model sitting here staring you in the face. Okay, if you take the 12 centimeter magnitude of the r vector, of course this is a circle of radius 12 centimeters, and that's where I get it. From the axis to the rim is 12 centimeters, so r has a magnitude of 12 centimeters, which means that our perpendicular is the x component of that, and that's going to be the radius times the cosine of 300 degrees. Now, you don't want to say radius times the cosine of 60 degrees, although that would give you the same result. You want to say radius times the cosine of 300 degrees. And that's because if the angle was between 90 and 270 degrees, the cosine would give you the negative, and you don't have to think about whether it's positive or negative. You just use the magnitude of the r vector, in this case the 12 centimeters, times the cosine of the angle measured counterclockwise from the positive x-axis, and you get it. And you do that and you get 6 centimeters. Now, that said, you should know how to get the cosine of 300 degrees, okay? It does make an angle of 60 degrees with the x-axis, so you got a 30-60 triangle here whose hypotenuse is double this side, isn't it? And that kind of confirms it. But if you're using a calculator, you're going to use the cosine of the circular angle. Okay, well, okay, that's a lot said, but that comes out to 0.003 meter newtons. Now, what's the direction? Well, I'm going to break here, and we're going to start putting vectors on these things.